Good morning, everyone. So, as a quick catalyst to start today, I want you to think about the Red Rover activity that we did last week. During Red Rover, what do the following objects represent? The people holding hands and the hands themselves. How can we use this model to make a water molecule, like H2O? And how can we use this model to make an oxygen molecule of O2? So take a minute right now to answer these questions with your partners. Pause this video and go over them together before you continue and look over the answers. So pause the video, discuss with your partners to answer all of these questions. Alright, so you should have answered the questions. I'm going to go over the answers quickly now. So the people holding hands, the hands themselves, what do they represent in the game Red Rover? How can we use this model to make a water molecule using Lewis dot structures like we were doing last week? And what about an oxygen molecule? Well, the people in our atom for models in Red Rover are the atoms, of course, and holding hands are the covalent bonds that are connecting those atoms by sharing electrons. The hands themselves, since you have two of them in your covalent bond, sharing electrons are the actual electron pair. And we can use this model to make a water molecule using Lewis dot structures by having three people in a line that are holding hands, where the two people on the either side are going to represent hydrogen atoms. They're holding hands with the person in the middle, the oxygen atom, and sharing those electron pairs like we see in the Lewis dot structure. Oxygen's a little bit different, so we have to have two pairs of electrons in between the two oxygen atoms, and the way we would model that is by having two people hold both of their hands. That way they're sharing 4 electrons, 2 electron pairs, just like you see in the Lewis dot structure. And that's a little bit different from what we've seen before, but that's what we're going to talk about today. So there's a nice picture of holding hands that you can remember this activity by. A few quick announcements of the homework that you were given on Thursday and Friday after the benchmark, plus a little bit of an extra homework will be due this Wednesday. So this is when we're going to finish up our mini unit before beginning Unit 7, Chemical Reactions. And this is just a reminder that the homework due on Wednesday includes Lesson 12 that we did on Thursday and Friday, and today's lesson, Lesson 13. So here's your agenda for today. You're going to have a quick discussion with this video lesson and talk a little bit about octopi, the plural for octopus. They're crazy. So in the PowerPoint link, there's a link to a video that I want you to check out. When you click on octopi are crazy, then you probably won't have time for your activity. So instead, you'll just be practicing with stuff that we worked on for this discussion before starting your homework. So, still talking about Unit 6, chemical bonding, and today we're going to talk something about the Octet rule, which has to do something with the octopus video that I mentioned earlier. Answering our essential question, how are atoms connected to each other with Lewis dot structures? We started talking about things that look like the picture on the left with CH4 or methane, and a little bit about carbon dioxide, CO2, like you saw in the other picture. And by the end of the lesson, you want to be able to say, I can apply the Octet rule to construct Lewis dot structures for molecules with covalent bonds. So using the Octet rule with our Lewis structures, like we started doing. And I can construct Lewis dot structures for molecules with single, double, and triple covalent bonds. So that's something we want to add to our toolbox too. Here it is, the Octet rule. And to start talking about the Octet rule, I want to ask a question. How many legs does an octopus have, like that cute little octopus at the bottom right? The answer to that is 8. And you'll see this little part octo in octopus. That's what tells you that there are 8 legs on an octopus, because that prefix oct means 8. So if we have an Octet rule, that says that atoms transfer or share electrons to have 8 total valence electrons. Again, atoms are going to transfer or share their electrons to have 8 total valence electrons. Why is that going to happen? Well, two reasons, basically. The first one is that they want to resemble a noble gas. And if you remember, Lewis dot structures for noble gases that have 8 valence electrons have 8 total valence electrons like that. So they want to resemble a noble gas. Why do they want to resemble a noble gas? Because they want to have a full outer electron shell. And that would mean having 8 valence electrons. So, for example, if we make a chlorine molecule, to make Lewis dot structures for this molecule, following the octet rule, we have to do a few things. First, we have to draw each atom's Lewis dot structure. And in chlorine, there are 2 chlorine atoms. So I'll put those down there. And they have 7 valence electrons, which means that I have to draw the first ones unpaired, going around clockwise from top, then right, bottom, and left. Then I can pair them up again at the top, right, and bottom. And the second chlorine is going to have the same Lewis dot structure that looks like that. Next, we want to count the total number of valence electrons, and that's going to be important because we don't want that number to change. So the first chlorine has 7 valence electrons, the second one has 7 valence electrons also, for a total of 14. Next thing we want to do is form our covalent bonds. By pairing up the unpaired electrons, I'm going to draw those in blue down here. So chlorine, each one has an unpaired electron. And we want to pair up those unpaired electrons to form covalent bonds. The way we're going to do that is by drawing the chlorine atoms next to each other and putting those unpaired electrons in between them in the center right there. So now we have our paired up unpaired electrons in blue between our chlorine atoms. Next thing you want to do is draw the rest of the valence electrons around those chlorine atoms, because you don't want to forget them. Because like I said, we don't want the total number of valence electrons to change. So again, you'll count the total number of valence electrons again to make sure that they haven't changed. And yes, now we still have 14. So finally, we want to figure out if we satisfied the octet rule. And according to the octet rule, each atom wants 8 valence electrons around it. So if I look at my chlorine atom on the left, around it you'll count 8 valence electrons, so that one satisfies the octet rule. And on the right, if you look at just the electrons that are touching the chlorine atom to the right, you'll see that it also has 8. So good job. Well done. Again, I want you to pause the video and try the same process with this water molecule with your partners. So draw each atom's Lewis dot structure, count the number of total valence electrons, pair up those unpaired electrons, count the total number of electrons again, and check if you satisfy the octet rule. Pause the video, try this out with your partners, and I'll have the answer for you in 5 seconds. Okay, so water molecule has 2 hydrogens and an oxygen. The hydrogens have 1 valence electron, the oxygen has 6, so the Lewis structures will look just like that. And the total number of valence electrons are 8. 1 from each of the hydrogen atoms, and then 6 from the oxygen atom, sorry. Those unpaired electrons drawn in blue are 1 on hydrogen, 1 on the other hydrogen, and 2 on oxygen. And now we want to pair them up to form our covalent bonds. But a question we have to start answering is, which atom do we want to draw in the center? And I'll tell you that the central atom of your molecules is going to be the one that can make the most covalent bonds. So in our case here, that's oxygen. I'll draw the hydrogens on the side with oxygen in the center. The unpaired electrons from hydrogen are going to pair up with the 2 unpaired electrons from oxygen, and I'll pull over the other 4 valence electrons from oxygen for a total of 8. And did we satisfy the octet rule? Well, oxygen has 8 valence electrons. Both of the hydrogens have 2. That's not satisfying the octet rule, but this is still correct, and I'll tell you why in just a second. That's because hydrogen is an exception. Hydrogen and helium can have 2 valence electrons and still be happy as if the other atoms had 8. Why? One reason. That's because those 2 valence electrons fill the n equals 1 shell that hydrogen and helium have electrons in. The n equals 1 shell only has 2 electrons, so it'll be full with just 2 electrons, and that's okay for hydrogen or helium. Beryllium is another exception. It can have 4 valence electrons, and boron can have 6 valence electrons. Why? We're not going to worry about it, so just take my word for it that beryllium can have 4 and boron can have 6 valence electrons. So an atom's unpaired electrons are available for sharing and forming covalent bonds. We already talked about that. And there's a bit of a pattern that we talked about a little bit in class called the Honk 1, 2, 3, 4 rule. That tells you that hydrogen can form 1 covalent bond with oxygen, or different atoms, Oxygen can form 2, nitrogen can form 3, and carbon can form 4 covalent bonds. That's because that's the number of unpaired electrons that each one of those atoms had. So if you put it in order, hydrogen can form 1, oxygen can form 2, nitrogen can form 3, carbon can form 4. And why is that? Well, just like we've been saying, that's the number of unpaired electrons. Another thing I want to mention is that I said you want to put the atom that can form the most covalent bonds in the center of your molecule. So think about what that would mean for which atom would go in the center of molecules according to our Honk 1, 2, 3, 4 rule. But some atom combinations cannot satisfy the octet rule with single covalent bonds. And carbon dioxide, CO2, is one of those. We'll talk about how and why in just a second. Instead, they have to form double bonds, and you're going to have 2 valence electron pairs for a total of 4 electrons in a single bond, and a triple bond, which will have 3 valence electron pairs in 1 bond. So these atoms that can't satisfy the octet rule with single bonds alone will form double and triple bonds. So what does that look like? For carbon dioxide, we want to follow the same steps that we've done before. Draw the Lewis structures for carbon, oxygen, and the second oxygen. Count the total number of valence electrons. You'll see that carbon has 4, both oxygens have 6 for a total of 16. Now pair up those unpaired electrons to form covalent bonds. We know that carbon has 4 unpaired electrons and both oxygens have 2. Remember I said the atom with the most unpaired electrons is going to go in the center. That's our carbon atom, and we'll draw the oxygens on either side. And carbon has 4 total unpaired electrons, but we only have 2 other atoms to pair them with. That means we're going to share those 4 electrons with either oxygen. And the oxygens will contribute their 2 electrons to this bond to make a double bond. So there are 2 electron pairs for 4 total electrons between each one of the oxygen atoms and the carbon atom. That is a double bond. So again, count the number of total valence electrons. Did we satisfy the octet rule? What about the Honk 1, 2, 3, 4 rule? Well, our total number of valence electrons is still 16 because we have 8 on the left side of the carbon and 8 on the right side of the carbon. That makes it easy to see we're satisfying the octet rule because the oxygen over there has 8 total valence electrons. Carbon in the center also has 8 total valence electrons, and oxygen on the right has 8 total valence electrons. And the oxygen is bonding with 2 different atoms. Both of those atoms just happen to be the carbon atom. Carbon is bonding with 4, 2 with either oxygen, and the oxygen is bonding 2 covalent bonds to carbon. So we are satisfying the Honk 1, 2, 3, 4 rule. So last example we'll go through together. I want you to try the same thing with nitrogen. So pause the video, try this same process with nitrogen, and I'll give you a hint. You're going to have to include either a double or a triple bond to make it happen. Alright, so same thing. Draw each atom's Lewis dot structure. We have 5 valence electrons for each of our nitrogen atoms, and that is 5 plus 5 for a total of 10 valence electrons. Now we want to pair up our unpaired electrons. Each nitrogen atom has 3 unpaired electrons. So we'll put them right next to each other and put the 3 unpaired electrons from each nitrogen in between our nitrogen atoms. If you count it up, you'll see there's 6 total electrons between them, and that is 3 electron pairs, forming a triple bond. So count them up again to make sure our number hasn't changed. 2 plus 6 in the center plus 2 at the right is 10 total valence electrons. And our nitrogen on the left has 8 total valence electrons, satisfying the octet rule. Our one on the right also has 8 total valence electrons, satisfying the octet rule. Hunk 1, 2, 3, 4, nitrogen will form 3 covalent bonds with other atoms, and in our triple bond, we essentially have 3 covalent bonds between the 2 nitrogen atoms. So that's it for our discussion. Make sure that you click the link in the PowerPoint to see this video, that octopi are crazy. And remember, octopus, 8 legs, octet rule, each atom wants 8 electrons. And you're not going to have time for this activity, we're going to skip that. Some wrap-up discussion points. So the hunk 1, 2, 3, 4 rule and the octet rule both help you figure out Lewis dot structures. Both the hunk 1, 2, 3, 4 rule and the octet rule can be satisfied by using double and triple bonds appropriately. It's not possible to create a triple bonded oxygen compound according to the hunk 1, 2, 3, 4 rule, and you can figure out why that is if you think about it a little bit. But there are exceptions, specifically for hydrogen and helium. They're happy with just 2 valence electrons. And don't forget to make the central atom make the most bonds. That'll make your Lewis dot structures work out nicely. So, to answer our central question, how do atoms bond to form molecules? Well, elements will form covalent bonds by sharing electrons until each atom has 8 valence electrons, according to the octet rule. Hydrogen is an exception. It forms bonds that have 2 valence electrons. Atoms can form double and triple bonds, and when covalent bonds form, each atom resembles a noble gas in its electron configuration. So to practice this a little bit more and make sure that you're in good shape for today, I want you to, in your science journals, draw the Lewis dot structure for ozone, which is O3 with 3 oxygen molecules. Make sure you follow the same process that we've been doing in the other examples, and I want this to go away, but make that go away. But we're going to do this with claim, evidence, and reasoning. Keep practicing this. So draw the Lewis dot structure for ozone to satisfy your claim and answer the question. Then draw the Lewis dot structure for oxygen alone and circle the unpaired electrons for your evidence. For your reasoning, I want you to state the octet rule and the hunk 1, 2, 3, 4 rule and explain whether your Lewis dot structure for ozone, O3, satisfies those rules. When you finish, answer the questions 1 through 9 from the octet rule reading that you got after the benchmark on Thursday and Friday in your science journals. So both of these questions I want to see in your science journals, and this is for homework due on Wednesday. That's it. We'll talk about this a little bit more on Wednesday before beginning our unit on chemical reactions.